Click it once. So, okay.
It's okay, I follow.
Great, wonderful. Hello, everyone. Welcome to our final CU Prime talk of the semester. So if you haven't heard of CU Prime before, we are a group that's devoted to diversity, equity, inclusion within the physics department here on campus. And so we do that in a few different ways. We have a mentorship program. We have a class that we run each fall. And then one of the ways we also do that is through this talk series. And so we try to invite graduate students like Garrison here to talk about their research in a jargon-free way and help us see what it looks like to do science at the graduate level and beyond. So if you are here in person, then welcome. We have plenty of pizza. Be sure to sign in on those laptops if you haven't already. And if you're joining on live on YouTube, then welcome as well. So I will let you take it over, and then if at any point you have questions, feel free to interrupt and ask them. And yeah, take it away.
So as Tyler mentioned, my name is Garrison, and I'm going to tell you mostly just about what superconductors are, but if we have time towards the end, we'll get to some of my work on far from equilibrium searches for what's called room temperature superconductivity. So let's dive in and see how far we get. Before we dive into superconductors, I just want to give ourselves a reminder of like what a conductor is and how to think about those. So maybe you've seen something called Ohm's law, which is a famous law that sort of describes metals, right? And here's what is admittedly a very terrible analogy for these voltage relating to current and resistance. So in this case, you can think about like the voltage is sort of doing the work of pushing the current along, which is sort of being resisting movement because it's being moved, in this case, up an inclined plane. Most definitely not the case for actual wires, but it's something of a reasonable analogy. I'll also remind you that, of course, electric fields sort of apply forces on current charge and sort of cause charged particles to accelerate in their presence. Voltage is closely related to an electric field. It's just the electric field sort of times the distance over which it's applied. But the essential thing here is that the voltage and electric fields are accelerating charge, and then current is essentially the amount of charge you have and times some velocity with which it's moving, which sort of, if you take a second to think about Ohm's law, brings about a puzzle that I believe historically was a big puzzle in the field, something in like the 18 or 1700s when they were first discovering things like Ohm's law, which is that, I'm essentially applying some force and I'm getting a constant velocity from a constant force. And of course, that's sort of an absurd thing because we know about Newton's law, which tells us a constant force gives us a constant acceleration, which would mean you would think that the charge would just sort of keep going faster and faster and faster as long as you're applying this force on it. But instead, what happens is somehow I apply some force and I achieve some constant velocity. So I'm going to ask you to discuss two things. The first one's going to be sort of why the charge doesn't just keep accelerating. Why do you think that's happening in materials in your actual wires? And then the other thing is very related, right? If I'm not just accelerating and running away, if the energy so I'm applying a force over some distance, that means I'm doing work. That means I'm dumping energy into my charge motion. So, normally that means going faster and faster, I'm picking up momentum or kinetic energy. But in this case, if I'm not going faster and faster, then, where the heck is that energy going? So those are the two things I'd like to give you guys a chance to sort of stop and think about and discuss with your partners. So maybe give you like a minute or two to do that.
Well,
Okay.
so charge that is.
All right, I think maybe people are quieting down a bit, so maybe there's some consensus. Does anyone want to like jump in and give me some ideas? Maybe let's start with the first one. Why doesn't it just keep accelerating? Definitely heard some terms in the right direction.
There is a counteracting force of some sort.
Yes, there's got to be some counteracting force ultimately. Can we say anything else about what that might be? Were there any,
Impurities in the wire or
impurities in the wire is a great idea. How would that be an issue?
well, we tried for months ago, but like keep hitting like these impurities and that would make it
That's exactly right, actually. And why do you think, where do you think that energy goes?
So like, oh, thermal?
Thermal. Okay, yes, that pretty much nails it on the head. So let's see. The first picture, what she was describing is that, these charges are sort of moving along under the presence of an electric field, and they're bouncing off of the atoms that are there and coming to a stop. So sure, they get accelerated, but then periodically stop, and then accelerate, stop, and accelerate, stop. And so that happens on a very, very fast time scale. So we actually don't even notice that. What we just see is some net drift velocity that sort of averages over this accelerating and stopping. And then, as you said, exactly right, that collision imparts energy into the motion of those atoms, which is manifested in heat. And so this is how, like, your ovens have those coils that heat up. That's exactly what they're doing. They're driving lots of current through a very resistant material that heats up and then heats your oven. So I guess the point here is to remember that a normal conductor obeys Ohm's law. Better metals like copper that we make wires out of have lower resistance, which means it's easier to move current along. It's worth noting that power loss is linearly related to resistance. So lower resistance, lower power loss from transmission. And then microscopically, that's exactly the right picture. You're sort of accelerating along and then colliding with things and sort of bouncing off of things, and that's why you're losing energy, and that's why you have resistance. Okay, so
So how do light bulbs work in terms of they glow instead of necessarily producing? No, I guess they produce.
Well, right. I think I guess the right way to, that's an interesting question. I'm pretty sure the right way to answer that question is that they're just hot. Like, as you get hotter, you radiate with higher frequency light. Like thermal radiation is just sort of like microwaves, kind of lower different frequency light. But eventually, if you get hot enough, you'll radiate in the visible spectrum. And so this is the same thing that's going on here. That's why it's glowing orange. So it's that heat dissipating through electromagnetic radiation. And eventually, if you're hot enough, you radiate invisible. I don't know if that's super helpful or not, but in any case, if we want to talk about now superconductors, as the name implies, they conduct extremely well, which means they have zero resistance, and that's what's very interesting about them. So they were first discovered by sort of cooling down metals, and so this is sort of what we were talking about before. You have these electrons bouncing off of these atoms as they try and move along, and this is Ohm's law. These are metals. As you cool them, the molecular motion sort of slows a little bit, so the resistance goes down, but it's still finite. But eventually they discovered at some temperature, it drops off and goes to zero. And this temperature, which it drops very sharply, is what we call the critical temperature. And below this temperature, you're superconducting. Above this temperature, you're not superconducting, often near a metal. This temperature, as it turns out, will be very cold. How cold? So you think the coldest temperature ever recorded on Earth, I guess, was at this place Vostok, Antarctica. I don't know if I'm pronouncing that right, at 184 Kelvin. It's quite cold. The moon at night is 120 Kelvin. These would be warm temperatures for a superconductor. Most of the superconductors are like well below 100 Kelvin. So we're talking really, really cold temperatures before you see the superconducting behavior. But sure enough, eventually it goes into this zero resistance state. And you can ask, how small is zero? Because always you're making some measurement, and measuring zero is traditionally very hard because you probably have some finite resolution. So one of the best ways to measure how small it is they put current moving around in a superconducting ring. They just started it going. And with a normal metal, it would very quickly, if you stop applying a voltage, stop accelerating it, it would just come to rest. But with a superconductor, it decays extremely slowly. So slowly, in fact, that you can extrapolate how long it would take for it to come to complete rest. And that's longer than the age of the universe. So the resistance is extremely small. Yeah.
How does lowering the temperature exactly like impurities?
So it's not going to remove the impurities, but we will come back to why this sort of gives rise to superconductivity, why the lower temperature is involved. But it's a more subtle point. But we're definitely going to come back to that. It's going to take us a few slides to get to that answer. But before we dive into that, of course, what we're after is a room temperature superconductor. And by room temperature, I just mean that this critical temperature is something like above 300 Kelvin, so that if I was setting this material in a room like this, it would be a superconductor. Unfortunately, that's not the case, and we'll be trying to think about if it's possible to make a room temperature superconductor. But before we go into that, we should always motivate, why do we care about these things? So they have zero resistance. So I would ask you guys now to sort of step back and think about and discuss with your neighbors. If you had a room temperature superconductor, what would you use it for? Do you think these things are useful? What kind of ideas could you guys come up with for using these? Okay, so anyone want to jump in with their favorite idea? Yeah.
Electricity, power lines.
Power lines. You replace the grid. Yeah, that was one of the things on my little poster. We lose like 5% of power to loss on transmission lines, so that would be very nice.
Or magnetic field based off of current, so it got a potentially higher current that wasn't restricted by like a resistance. We could do some stuff with that.
That's right. You could make larger superconducting magnets. These magnets could then just run forever and generate massive magnetic fields. Those are very important. Anyone have any idea what those are important for? Think medicine, MRIs. We already use superconductors in MRIs, but they require the liquid nitrogen to get to the right temperatures. And so that's part of the reason that they're so expensive and they're these big machines, right?
Yeah. Do you use that same technology that like the maglev trains do?
Yeah, maglev trains don't actually currently use superconductors, but I think actually Japan is building one that's maybe going to start using it. We were talking about this yesterday, but most maglev trains don't use superconductors, but you certainly could use superconductors to do something very similar. So I think you guys mostly hit everything I was going to say. Better electrical grid, levitating vehicles, maglev trains, electrical motors would just be more efficient with superconductors. MRI machines we touched on. These devices, these superconducting quantum interference devices, or SQUIDs, are maybe a less obvious use for superconductors, but it turns out you can measure magnetic fields extremely precisely with these particular devices made out of superconductors. And there's also more exotic things, like maybe you guys have heard of quantum computers, and there's like this interest in quantum computers. Well, topological quantum computers would exploit superconductors. And Google, for example, their quantum computer, if you guys saw that, that's all based off of superconductors. But they have to live in these massive dilution refrigerators and things to do that because they have to get cold. In any case, yeah. So as you can see, it's sort of not very hard to realize once you have a superconductor that this will be a very, very valuable piece of technology. But unfortunately, as we said, they're mostly not room temperature. So here I just wanted to show you like the progress in the field towards room temperature superconductivity. So here's obviously the timeline. The first superconductors were discovered in the early 1900s, and on the y-axis is the critical temperature. Obviously the first one's extremely cold, less than 10 Kelvin. They've sort of increased. There's different types of classes of superconductors. That's what all the different symbols are. I don't know if it's worth going into that, but we've steadily increased the temperature, but we're still very far below room temperature. I mean, even the ones that are getting closer at extremely high pressures, we'll talk about those later. But yeah, I mean, way colder than Earth, colder than the moon even is what, like around that temperature range. But we did break the liquid nitrogen. That was important. In any case, the point is they're very cold and we've made some progress, but we're still very far away from the room temperature of superconductor. Okay, but let's just now sort of back up and sort of try and understand what superconductors are after all. So the simplest answer is, okay, there's some superfluid of electron pairs, but that's really not a very simple answer either because it's just another set of jargon that's hard to understand. But I want to focus on that last part there, the electron pairs. And I want to try and unpack why we needed pairs of electrons instead of just electrons themselves. And this comes out of basically, quantum statistics. And so I'll try and help you guys understand what the differences are in two types of quantum statistics. All particles are either bosonic or fermionic. And so they have very different statistical properties. And these properties are very important to what makes a superconductor. So let's try and understand what these bosons and fermions are and why we have them. So first, I just want to have to introduce, and maybe some of you guys have already seen this anyway, but in quantum mechanics, you replace a particle's position and velocity with something that's called a wave function to describe the quantum particle, which is some function over some position x. And so, and then it turns out that the square of this function is the probability density for finding a particle at position x. So it's sort of illustrating what that looks like. Maybe you have an x-axis, and we have sort of the blue is the wave function, and the red is the square. And then you're sort of trying to see that this red ball is being found more frequently where the function is peaked and less frequently by the tails. So the important thing to remember here is that it's the probability that is measurable. The wave function itself is not measurable. Suffice it to say, I guess, that might be somewhat debated, but mostly you can't measure it. It's really the probability that you measure. So now I want to think about how this relates to identical particles and what happens when we move and manipulate these identical particles and add them up, and that's what's going to give rise to the statistics. So I want to try and introduce this idea of exchanging identical particles. So these red circles with an E inside of them, that's meant to represent, an identical particle. I guess in this case, I'm using an electron. So I have two electrons, and they're living in two distinguishable states, the blue square and the blue triangle. So I'm trying to distinguish here between the state that the electron occupies, which might be like an orbital around a hydrogen atom, right? And maybe I can tell that there's an electron around this hydrogen atom and an electron around this hydrogen atom. And while those states are distinguishable, I can tell the difference between the square and the triangle. The electrons that live in those states are indistinguishable. And that's a pretty good fundamental truth that we have. And so this gives rise to some very important implications when you think about what happens when you exchange these electrons. So I want to take the electron on the right, move it to the left, and the electron on the left and move it to the right, right? I want to exchange these electrons. And as you can imagine, when you do that, the whole point is the electrons are identical. So I get back a system that is unchanged by this exchange, right? So I can't tell the difference in these particles, so I can't tell the difference when I exchange them. Therefore, I should not be able to tell the difference in the probability wave function for the particles. So in other words, this psi squared as a function of x1 and x2, if I exchange x1 and x2, it's identically the same, right? But crucially, this means that the square, the thing that I can measure, which is squared, is the thing that I can tell has to be unchanged under exchange, right? But that gives us two options, right? If it's a square that's unchanged, I could have the wave function itself pick up a minus sign, or it could just itself be the same, right? Because the -1 squared is, of course, just 1. So this gives rise to two options, which will be our bosons and our fermions. So let's unpack the first option, where the wave function is itself the same. This is when we're looking at two bosons. It turns out that this bosonic fermionic behavior is related to this intrinsic property of quantum particles, which is called spin, which is maybe you've heard about it. We don't need to go into the details. You can think about it something like a mass. It's just electrons and particles carry this thing called spin, and they have different values. In the case of boson, they have integral spin values, and examples of these are like photons, gluons, and the force-carrying particles. So what happens when we exchange photons? Now we're thinking about the wave function, and the point is we can live in an identical square states, two identical square states with two identical photons occupying them. When we go to do exchange, of course, we just get back the same thing. Can't tell the difference. But now with fermions, the point is that we want to pick up a minus sign under this exchange. Fermions have half integral spin objects, like spin 1/2, for example, are electrons. And there's a lot of other ones, but that's the one we'll focus on. And it turns out this minus sign has very deep implications. And to help try and illustrate that, I'm going to give you a more extreme example of exchange. So here I have two electrons, and it's I'm labeling to help you sort of follow what's going on. I have an electron 1 in the square state, electron 2 in a triangle state, and my overall state is going to be that condition minus the condition in which the electron is in the triangle and electron 2 is in the square. And this minus sign is important because that's how I give rise under the exchange to the overall minus sign. So to see what's happening here, right, I just simply swapped 1 and 2, for example. Now I end up with a state with a positive sign in front of it where electron 2 is in the square and electron 1 is in the triangle. That is the same as this state, except it had a minus sign before, now it has a positive sign. If you think carefully through this one, you see the same thing. You have a minus sign, and this corresponds to this one where there's a plus sign. And so the point is, I very carefully chose to make this one a square and a triangle for fermions, and this one could be identical squares. Because if you think about it kind of hard, right, I can't put two electrons in identical states because there's no way for me to get back a negative sign under exchange, right? There's no way for me to write down something like this where when I exchange, I don't get back the exact same thing. So that means effectively that fermions cannot occupy the same state. They're forbidden from occupying the same, as you can't have two electrons in the same orbital around a hydrogen, for example, right? And that is because of this minus sign, and this minus sign is what we call antisymmetry. So it turns out this is going to be really important to get superconductors, but one more thing to see how that happens. I want to think about how individual bosons will behave versus how individual electrons or fermions will behave at zero temperature. So at zero temperature, we're going to try and find our lowest energy state, right? And if I'm bosonic and all of my bosons can go into the same state, all of my bosons are going to pile into the same identical lowest energy state, right? So that is going to mean that effectively all of my bosons occupy a single quantum mechanical state. It's this massive macroscopic quantum state. It's all unified in this collective behavior that emerges from it. And it's this unified collective behavior that's going to give rise to superfluids. And we'll try and help you understand why that gives rise to superfluids here in a little bit. But while I'm here, I feel like I have to connect this to what surely is physics majors. You guys have all seen this picture, right? Of course, Cornell won the Nobel Prize. He works here, if you didn't know that, for discovering the first Bose-Einstein condensate, which was the state in which all of these bosons piled into the same lowest energy state. You can see them sort of densely packed in there. So that's the point. Bosons, when they cool, they all go into the same ground state and they all join into one unified macroscopic quantum state. Now, fermions have very different behavior, right? Because they can't go into the same state. So I put my first electron in my lowest energy state. I put my next electron in my next lowest energy state, the next one in the next lowest, and so on and so forth, until all of my electrons have a place to live. This should sort of remind you of something like your little filling diagrams that you did probably in chemistry at some point. So like for lithium, for example, the first electron, of course, is in the 1s. The next one has to come spin down. The next one has to go to 2s. If these are bosons, all of those electrons just simply live in the same spin state in the 1s. But because they're fermions, they have to spread out like this. And in a solid, you have a very analogous thing going on. Although it's not atomic orbitals that you're filling, you still have a bunch of states that you successively fill up. And it gives rise to these terms, and these things are important for metals and for solids. So you have the Fermi C, which is all of the states that are filled. You have the Fermi surface, which is the highest energy state, and all of those various states that are at the highest energy filled states by electrons. And to give you a sense for how crazy this is and how distinct it is, if I just simply had one electron in a copper and I was trying to put it in the same state that the Fermi surface lives at, the temperature I would need to get that electron to go to that high of an energy state would be something like 80,000 Kelvin, right? So it's an extremely high energy states that you would never go to, except for this quantum Pauli exclusion principle forbids you from trying to find this lower energy states, right? And it's for this reason that you can't get into a single coherent macroscopic state, and you have no fermionic superfluids because of this. So it's for this reason that we need to make pairs, right? Pairs of electrons. So just suffice it to say, electrons come spinning one half. If I can form a bound state of electrons where I have a spin one half pointing in one direction and a spin one half pointing in the other direction, I add that up and I get something with effectively zero spin. Zero is an integer. So this pair is something like a boson. So while the individual fermions repel each other, these paired electrons are more bosonic, and they're happier to go sit in these macroscopic unified states and condense. So, but you should be asking yourself, why on earth would electrons form a bound state? And this was, for a long time, people kind of suspected that superconductors had to do with superfluids, which were from bosons, but they didn't understand how you could ever have a pair of electrons. And it wasn't until the 60s when a Nobel Prize was won by Bardeen, Cooper, and Schrieffer for figuring this out. So the point is, these electrons are not in vacuum. They live inside of these materials where they're these charged ions. And what can happen is one electron can come along, and it's obviously negatively charged, so it will distort the atomic position just a little bit, right? So it pulls them in, and then the electron's so fast it moves away, and the ions can't relax super fast. So it leaves a little residual region of positive charge, which then can attract in another electron, right? So in this way, we say that the electron pairing is mediated by this electron-phonon interaction. So phonon is the quantum mechanical version of this lattice vibration. So that's what these describe. So it's this lattice vibrations and distortions that can sort of mediate and act as attraction between two electrons to give rise to these pairs. And these pairs are something like bosons. And so the point is, yeah.
Would the fact that it has a positive charge once it leaves, it goes to the right continuously, pull it back and just slow it down?
Yeah, you'll get some slowing down, sure, but these electrons, so remember, because of the Pauli exclusion principle, they're really high energy states. That means they're moving quite fast, right? So they might be slowed down a little bit, but it's like a fast moving car hitting a puddle of water. I mean, I'm sure it slows down a bit, but it more so just displaces the water and moves on, right? But yeah, that probably is true to some extent. But in any case, the point here is that we have these pairs that don't have to obey the Pauli exclusion principle, so they can create this macroscopic, massive quantum state, and it's this collective behavior that gives rise to superconductivity. So I just want to remind you that the reason that there's resistance is because an individual electron comes along and it bounces off of things, and as it bounces, it loses energy. Now, I guess I want to try and give you guys a chance to sort of speculate why 10 to the 26 electrons all joining together into a single state would give rise to a zero resistance state. So I'll give you guys a second to sort of brainstorm on that, see if you guys can come up with a good idea. It's not an easy question. I'm sorry.
I guess maybe
Does anyone want to jump in with their leading suspicions? I definitely heard some things on the right track.
If all the electrons are together, they can kind of find the path of least resistance and all travel together.
So they're sort of working coordination to sort of avoid these atoms and such and get out of each other's way. I like that. That's a pretty good analogy. Anyone else got different thoughts or different ways to think about it? Okay, so I'll give you a couple analogies sort of in that vein for sure. So one way to think about it, my boss loves this analogy of the amoeba, right? So the amoeba compared to, say, a helium atom is so much bigger that it kind of just sort of like glides around the helium as though it's not even messing with it. Gotta say, I don't know if I personally love that analogy. This is probably the most precise, correct statement. If you have 10 to the 23 Cooper pairs all acting in unison to resist the superconductor, one has to scatter not just one electron, but 10 to the 23 electrons at once, right? So remember, one electron can bounce off an atom, but can 10 to the 23 electrons bounce off a single atom? And the answer turns out to be no, there's no way to do that and conserve energy and momentum. And so it just simply doesn't happen, which kind of in a way means that they're coordinated in a way to avoid ever colliding with anything in the first place. I like kind of this analogy, and I try to find better visualizations of it, but unfortunately there's nothing. I think you guys will be able to visualize it in your head. So if you think about traffic, right, you get all these cars on the road, and then someone hits their brake in front of you, so you've got to hit your brake, and then all of a sudden they're going faster, so you try and speed up, but then you got to slow down. Everyone's kind of speeding up and slowing down, trying to avoid having these collisions. But that would be like what a normal metal is like. And the comparison in my mind is something like this sort of far off future where we have these massive driverless cars, and we have this awesome 5G network that networks them all together, and they all work in unison, and then no one ever hits their brake or touches their gas unless everyone is doing it at the same time and in unison. So you never have these like incidental, accidental like speed ups and slow downs. Everyone just is on the exact same page. Those are sort of the best analogies I can give. But yes, somehow this behavior gets rise to zero resistance because they're all in this collective macroscopic state. One other important point on superconductors, I don't know how much I want to go into it, but sounds like at least some of you are familiar with it because you threw out the idea of maglev trains or floating things. So we talked about, this was the sort of the picture I have. It's a floating superconductor. This is a superconducting skateboard that floats because it's over a magnetic track. And this happens because superconductors, as it turns out, hate magnetic fields. The easy way to think about that is that, remember I told you that the only way to have a Cooper pair is these sort of opposite spin oriented guys or gals. And in a magnetic field, these spins won't orient one direction, right? And so eventually that magnetic field will force them to orient, and that breaks the Cooper pair and destroys superconductivity. At a large enough magnetic field, it will kill the superconductor. But you try to put in lower magnetic fields, the superconductor, because there's no loss to flow, the current can just sort of move itself around, slosh itself around to generate its own magnetic field that perfectly compensates the external magnetic field. And so a superconductor will perfectly screen out magnetic fields, and no magnetic field will be able to penetrate the superconductor. And so this screening effect is called the Meissner effect. And it's because of this and other subtle things that they will float stationary in the presence of a magnetic field. Yeah.
So why doesn't it counteract it if you have a big enough magnetic field?
Because eventually there's some energy. So there's the energy of them bound together, and that's some energy scale. But then there's also the energy penalty for being against the magnetic field, right? And that's if you've done magnetic dipoles. I'm pretty sure it's a linear magnetic field. So the larger your magnetic field, the larger that energy penalty for orienting perpendicular to the magnetic field. Eventually that energy exceeds the energy you gain from forming the bound state, and you break the bound state and become a ferromagnet, right? So it's these competing effects. But for low enough magnetic fields, the energy penalty for being against it is less than the energy you gain from forming a bound state. So you stay a superconductor. Yeah. Oh yeah. I don't know the exact numbers, but it could support trains, right? It can be quite large. So there's all kinds of ideas for and it's much cooler than a maglev train because it's not just like a repulsion that balances you pushed away. It's actually a locking in three-dimensional space. So you can hold it upside down. You can hold it, parallel, right? So you can imagine making three-dimensional frictionless joints and I've heard people talk about manufacturing processes. Maybe you could have these types of things, but it can be quite strong. I don't know the exact number, but yeah, it's certainly strong. Okay, but this is the Meissner effect. It won't come up much more. I just wanted to mention it because it's an important aspect of superconductors. Okay, but now I want to get back to finally, why the heck these things are so darn cool. So I mentioned it took us, until the 60s. I think we discovered them in the early 1900s to find a theory, but eventually we did. And this is sort of what the theory told us was that first of all, the critical temperature is related to this delta zero. And it also told us what that delta zero is related to. So let me unpack each of these terms. First of all, delta zero, that's the bound state energy of that Cooper pair. So it's the energy that the system gains by going into that bound state. It's also the energy it takes to break apart that Cooper pair. And like I said, it sets the TC. So higher TCs come from higher energies or higher delta zeros, lower delta zeros, lower TC. Now on the right-hand side, one of the first things you see is this h bar omega d. H bar, if you haven't seen it, it's just a fundamental constant from quantum mechanics. The omega d is a frequency of the lattice vibrations. And h bar omega d is the energy scale of those lattice vibrations. So this sort of defines the amount of energy involved in causing those phonons to vibrate. And similar to delta zero, larger h bar omega d, faster vibrations, you end up with a higher TC, and then vice versa. And just to give you a sense for the energy scale of h bar omega d in a typical material, we're looking at a temperature scale of 200 to 400 Kelvin. So if that was all that was there, it was just the 2 h bar omega d, we'd be in business. We would have room temperature superconductors. But unfortunately, what comes along for the ride is this exponential that really hurts us. In that exponential is this V0. V0 sort of characterizes the strength or the effective energy scale of the attraction between the electrons that is felt. Again, larger V0, higher TC, smaller V0, lower TC, and that kind of makes sense. As V0 goes to 0, what we're saying is there is no attraction between these electrons, so there should be no superconductors because there are no Cooper pairs. And that is, of course, borne out in this equation because it becomes an exponential to the negative infinity, and that's 0. So that sort of makes sense. And then finally, this rho F is just the number of electrons at the Fermi energy. So this is the number of electrons that live out there in the highest filled, most energetic states. They're the ones that are going to form pairs and sort of condense and go into these superfluid. So again, higher rho F, larger TC, and vice versa. So when exponentials work for you, it's awesome. We've seen the power of that with like Moore's law. When they work against you, it's a lot to overcome. And that's why the temperatures are really quite small, because they're exponentially suppressed by that exponential factor. But the important thing that I want you to take away from this is not the math of the equations, but there are effectively 3 things involved in superconductors, at least the types that we understand well. 1, the energy scale of those phonons or lattice vibrations. 2, the strength of the attraction between the electrons. And 3, the number of electrons near the Fermi energy. And so those are the 3 knobs that we have to tune to try and increase our TC. So I want to revisit this chart, right? And I want to call your attention, obviously they were doing, I don't know, lots of different research, tons of money, thinking about ways to manipulate these and find higher temperatures. But I want to draw your attention up here to these high pressure systems. And I want to point out actually that like last year, maybe 2 years ago, was a really important discovery where they claimed they found room temperature superconductivity, but at extremely high pressure in those types of systems. But actually, as it turns out, this is hotly contested. And so now I actually don't know if I should believe the measurement or not. But anyway, it's a whole field, this high pressure systems. And we're going to talk about why. But I want you to notice that all of them have hydrogen in them. And that's one of the main reasons they get such a high TC. Yeah.
Intuitively speaking, at least from like thinking about like gas laws, where if you increase the pressure, it would increase the temperature. I'm assuming that we're going to go into like how does increasing the pressure increase the temperature at which it can go superconductive?
Yeah, so I must confess that when I first thought about this, I was like, oh, that's obvious, right? Like higher pressure, that's more energy, then it requires more energy to vibrate under more pressure. And so that's raising that energy scale of the H bar omega D. That's all it is. That's just high pressure gives me higher energy scale phonons. That gives me higher TC. Then I prepared to do this talk, and I was like, I should obviously look that up. It turns out that I was completely wrong. And that while it is true that the energy scale goes up, the attraction goes down, and the rho F changes, and the behavior of TC just because of the pressure is really non-trivial. And there's a lot of different things that can happen. And so it's not so clear that like, oh, increasing pressure is the reason that we get a high TC from these systems. But let me show you on the next slide why we do get a high TC. But I want to emphasize it really comes down to the presence of the hydrogen, right? And the way to see that is remember there's this frequency omega t, and that should remind you of something like a simple harmonic oscillator. Maybe you guys have seen these little oscillating systems. And not necessarily deriving this omega t, it's more complex, but just from our understanding of a harmonic oscillator, we know that that's sort of like inversely related to the square root of the mass, right? That's why violins are higher pitched, they're smaller objects. Basses are much bigger, they're obviously lower pitch. You have flutes, again, small objects versus tubas. And so this lower mass should give me a higher frequency, should give me a higher energy scale. And so that's the deal. They're trying to take hydrogen because that's literally the smallest mass atom we can find. Let's make a solid out of that. And its vibrations will be really energetic. Also, hydrogen, if it was in a solid form, right? Basically, hydrogen without its electron is just a proton. Those strongly attract electrons. So there'll be a very strong attraction to the electrons when these hydrogens start moving. So V0 should be large. So that gives us hope that this will create a very high temperature superconductor. But the answer to your question on pressure, as it turns out, just comes down to the fact that hydrogen is gas and it doesn't form a solid. So you have to put it first with another molecule to sort of start to get it to want to coalesce, but then you still have to put a massive pressure to get it to solidify into something that has lattice vibrations and all these things in superconductivity. So it turns out that's why the high pressure and the pressures are very large. They're like on the order of that in the center of the Earth. So you've traded one impossible problem for another impossible problem, but it's, we learned a lot in the process, and that's pretty cool. And people are claiming that maybe there'll be ways to bring that pressure down. I don't know. But anyway, the point is, you think, okay, well, sort of inspired guess, I want to manipulate these energy scale of the phonons. So one way to do that is with pressure and with using different atoms and this kind of stuff. Another way to do that is with really strong time-dependent electric fields, or in other words, lasers, right? And so that's where we're headed. That's where we're now going to transition a little bit into my stuff. So first, I want to motivate it. Most of the inspiration comes from the work from a team led by Andrea Cavallari, and I should say he's one of these big shots who has many, many, many people who worked on his work, and we should probably recognize the students and postdocs who did all the work, but anyway, it's easier to put his name, so I guess it's how it goes. Anyway, so he looked at one particular, or he looked at really several, but the one I want to focus on is a particular superconductor called YBCO, and really all you need to know about this material is that you have these sort of layered structures, right? You have this blue and red two-dimensional layers. You have two layers closely spaced, one layer further spaced, or two layers further spaced from the other two layers, right? So what happens is we know very well that the superconductivity happens in the plane, and the planes that are closely spaced together couple very strongly. The planes that are further away, as you would imagine, couple less strongly. They're more independent of each other. Now, there are these oxygen atoms that live in between the planes, and the oxygen atoms, exactly where they are, how close they are to the planes, turns out to be very related to TC in these materials. And so he just sort of took an inspired guess of like, well, what if I come in with a really ridiculously strong laser, and I start making these oxygen atoms oscillate very strongly between the layers. And so in this way, he's sort of manipulating these lattice vibrations or these phonons with light in a very time-dependent fashion. I guess I forgot to mention it, but one way to think about it is like this is what a laser pulse you can imagine looks like. The electric field is oscillating and becomes very large, and it's a very short pulse. And as it enters your material, it distorts the atoms because, of course, they're charged ions, so they respond to these electric fields. So anyway, he's driving these oscillations, and he has some story. I don't know if I need to go into his story, because not a lot of people necessarily believe it. But in any case, he has stories for why he thinks this increases the TC of superconductivity. More importantly, as an experimentalist, he has measurements that kind of look like superconductors. And so here, we don't need to go into the phase diagram too much. This is what the labeled part of superconductor is, the equilibrium superconductor. But what the white dots are showing you are where the temperatures at which he's seeing what looks like a superconductor according to his measurement. And most crucially, he's seeing it in some cases, almost up to 400 Kelvin. It's very much above room temperature. So if it turns out this is true, if you believe him, the team has found room temperature superconductivity by driving systems with really intense laser pulses. So this is where I start to come in. Science needs confirmation. There's not been any replication really, and we're not trying to do a simple replication. We're doing a different technique, but Cavallari's technique, he did not measure zero resistance. He did not measure the Meissner effect. Those are the two things that define superconductivity. He measured other things that are consistent with the superconductor, but don't guarantee a superconductor. So for one, he might just be confused about what he's looking at. For two, it's not like he just makes this measurement and it's very trivial, like obvious, green light turns on superconductor. He has to take this complex data and manipulate it and extract from it and sort of try and understand what it says. And his analysis is not trivial. So, he's doing a lot of complex things. And so for either one of these reasons, you might just wonder, like maybe the team over there is just confused about what they're seeing. And so we want to try and confirm, and that's where my team enters. I think I'm running tight on time, but I will try and go through what we do. The experimental technique that we do is called photoemission spectroscopy. So Einstein won his Nobel Prize because he understood the photoelectric effect where you send in a photon and an electron can get ejected from your sample. In the modern days, we can very precisely control these photons, and we can very precisely measure the electrons that come out, both the amount of energy that they have and the direction at which they come out, which tells us the momentum it has. So a schematic of what this looks like is you have these electrons sort of living in these various energy states. Here's your Fermi energy, right? The point at which no real electrons live above it. And then you shine some light on these electrons and you eject them and sort of make a copy of the density of states above EF. And this is what you measure. And because of energy conservation and because you know the energy of the photons, you know what you had in your material. Similar story with momentum. So the point is you need really high quality interesting samples. You need light sources that are a real pain in the butt. You go all around the world to get these massive light sources. You need electron analysis, which is its own pain. You have to put all these things together on the right day and hope that the stars align to actually get data. And when you do, it's kind of cool. Most of the time, it's not. So this is what the system looks like. This is the ARPES system. The sample lives in here in cryogenic temperatures at pressures that are lower than your solar system. And they get ejected out and they go into this hemisphere. And we sort them and detect them with a camera. And that's the detection scheme. And on the back, behind these little plastic curtains, is a whole behemoth laser system that gives us our light. We put all this together to do angle resolved photo emission spectroscopy. That's just saying we can figure out the energy of these photo emitted electrons, and we actually know the angle at which they came out. So that's the technique that we do. And this is what, when everything works, this is what your data looks like. This is actually from our group, but it's from a much older student than myself. But here that he was doing ultra fast pump probe ARPES. So let me unpack that. Ultra fast is because we're using laser pulses that are themselves at time, picosecond scale. To give you a sense for that, your computer chips, they work at nanoseconds scale in terms of changing from zeros to ones. That's pretty darn fast. That's still 1,000 times slower than a picosecond. And we can even do sub-picoseconds. So this is ultra fast pump probe. So remember, I'm talking about pumping the system with a laser that excites these molecular motions inside your material. So that's your pump. But then you subsequently want to measure what's happening. That's your probe. And what you do is you have two light pulses, and you can control the relative time at which they arrive. So you can let your probe get there before your pump is even interacted with your system. That's these negative times. When they arrive at the same time, that's your zero time. When you get the positive times, that's because the pump has come and you're coming 3 picoseconds later with your probe, right? And so in this way, you can create successive images of what's going on at various time scales. And this is the energy of the electrons coming out. Now we backed out and put them within the material. So 0 here is the Fermi energy, and then wherever they live, the red is mostly where the electrons are, say. They don't really live where it's blue. And so what they're doing here is actually in a lot of ways the exact opposite of what I'm hoping to do. So they're measuring a superconductor. I know it's a superconductor because we talked about how electrons will fill up to the Fermi surface, but there are no electrons up to the Fermi surface. That's because when I kick an electron out, in this case, I need to first rip it apart from its partner and then out of the system. So that extra energy to rip it apart from its partner is the gap between where I actually measured them and the Fermi energy. And that's exactly this delta 0. So we can directly measure that delta. And what they did is they took a superconductor, they hit it with a laser pulse, which broke the superconductor. So now I have states coming through the Fermi energy, and they watched over time as it recovered back to a superconductor. We're hoping to do the opposite. We're hoping to look at a material that's not superconductor, hit it with just the right light, make it go superconducting, and then watch it recover over the course of what we expect to be a picosecond or a few picoseconds. Yeah. Yeah, so in this case, what they're doing is they're shining light on it, and they're not exciting the right modes, we hope. So they're exciting a different lattice vibration that doesn't necessarily play a role in superconductivity, but that heats up the electrons. So now I just dumped a ton of energy into my electrons with that laser light. The temperature goes way up, and now I'm way above TC. And then literally over time, my electrons cool, and because it's my sample is attached to a piece of copper that is itself attached to a cryostat or liquid helium. So I heat sink it, and eventually it cools back down, becomes a superconductor. So in this way, they really, at the end of the day, they heated it really fast and then watched it cool and come back to a superconductor. So it's similar to what we're doing, but we're hoping that with just the right light hitting just the right thing, we will actually see the superconductor. So it looks like I'm actually roughly going to finish on time. I'll sort of wrap up here. The whole point is we want to do time results to ARPES to confirm this superconductivity in this non-equilibrium fashion. The reason it's non-equilibrium, right, is because it goes to this other crazy state that is not just defined by, at a constant temperature. It's very strongly perturbed by these laser beams. And so I just want to point out a few things. First of all, this is my motivation. This is my goal. This is what I'm hoping to do. But for one, I'm almost certainly going to fail. And that's sort of the nature of science. I'll maybe define what fail is, to be fair, here in a moment. But I just mean that to say, look, if I do all the same work, if it happens to be that this person really did measure a superconductor and we manage to pull off this measurement, we'll see that. It'll be a big deal. It'll open a lot of doors. I do all the same work and it turns out that I'm wrong. I don't see anything interesting. It won't work. It won't open those same doors. It won't be as interesting because, while we like to believe that novel reports and replications are important and noble pursuit of science, they do not bring in millions of dollars and they do not necessarily make careers. For me, that is one of the biggest challenges of working on a project like this. How do you come in every day and be like, let's chug away and put my whole heart and soul into this thing that is maybe meaningless and never going to work, and nothing else is the point, right? I mean, I'm not kidding. I have a lot of friends who deal with the existential stress of you're confronting failure over and over again. Now, the alternative is that you can choose more modest projects that aren't, necessarily trying to do this great, huge, cool thing. They're just trying to do this slightly new thing that's slightly different and, therefore publishable. But it's, then not as interesting, right? And usually it's less risk to do that. And I do have a publication that I would say is more in that regime, much less interesting, but at least it gets you moving towards a PhD and graduation. So, if you go into PhD, you want to think about these projects, managing your risk and balancing big projects and little projects and, sort of thinking about the trade-offs. But I also want to come back to, this is my motivation, this is my goal, this is the cool story that you guys get to hear. It took me, an hour to say it, but, in reality, it has almost nothing to do with what I actually do, right? It's the inspiration. What I actually do is fix broken equipment, deal with plumbing issues, deal with mechanical systems that break, deal with vacuum systems, and I got a leak check because for some reason they started leaking. I've got electronics that break. You got to fix the solder on those things. You got to go design your optics. Whatever the heck comes up, you've got to do some engineering, some software, some data science. Sure, it's all motivated by physics, but do I really need to know physics to do 90% of what I do? I don't know. Certainly none of your classes teach you any of this stuff, right? No one, even though most of my time is data science, no one taught me how to install Python and deal with data. That's just what you do. So I don't know. I think I think everyone at some point in their PhD sort of, finish the classes and then get to the work and it's man, it seems like a little bit of a bait and switch. Now, I'm sure that the physics is way more important for some people. I'm sure that the professors need to know the physics. I'm sure that if I had a career as a professor, I would need to know the physics. But, maybe I will actually get data and then I will need to know the physics to try and understand what that data means. But, if I don't get data, I will never need that. So I just want to come back and say, okay, it's a bit dramatic to say it's a failure. You have to try and define your own notion of success. It's sort of hard to deal with in the sense that I set out to do this thing and I didn't do it. It's a failure. That's heartbreaking. But in another sense, I learned how to do all those things. I developed a lot of skills. What median starting salary for someone with a PhD if you leave physics and go into the private sector is well over 100K. So, failure is definitely a relative term here. But it's still, you might feel a little disappointed if you pour years into something that doesn't necessarily produce anything. So I don't know. Hopefully that doesn't happen for any of you, or me. I don't know. We'll find out. But with that, I guess I'll hit the last slide and call it a day.
So as usual, we have this link if you want to provide feedback on this talk. It's just a quick Google form. You can scan that QR code or go to the tiny URL. And yeah, if you're interested in giving a C prime talk, too bad, it's the last one of the semester. But we'll definitely need people for next year. So if you're still around next year, definitely come by and we'll see you then. So we have time for plenty of questions if you guys have any for you guys.
Size versus I'm sure like Apple and other companies would benefit from superconductor.
I think the moment it became room temperature, it would become commercial. But no, I mean, it's an interesting question. You always have to like justify to people, like, why are you giving me millions of dollars, right? And you usually need to have a pretty good answer for that. And statistically, usually that's unfortunately military, technological applications, or maybe we care enough and want to know about this basic science. Yeah, I mean, people, when they do research in superconductivity, I'm sure they always have a blurb about, oh, this could revolutionize the world, right? And then you go, but I'm really just trying to like make this little change, right? So I don't know, you're a little insulated from that as a student, but professors, for sure, that's how they bring it up. I have no idea what my boss's overhead is, but I think it's safe to say 7 figures a year at least. And that's supported by taxpayers, many of whom don't believe in science at all. But we have to justify it. So I think you always, if you can spin it into like, hey, this will be important for our strategic defense or for our technological advances in medicine and other things, that helps. That's why the NIH, is way more funded than physics, I think, right? Because like a lot of people care about living longer and healthier. It's all you first.
Is this a solo project? Do you have a team?
That's a good question. It's come and gone. When this particular project was directly funded, there were 3 of us locally working on it. The grant was aggressively promised a lot of things, and so it didn't get renewed. But my boss was still very interested, so we continued on. But I would say at this point, I'm working fairly independently. One of my others, the other 2 people who were initially working on it have moved off to other things, whereas I've tried to stay focused on it. But lately, another student has come in and started to be roped in on some aspects, but she's sort of been to a lot of different things too. But largely independent, but definitely with some people. Sometimes people were like fully in the trenches with me, and other times people have just sort of been there to talk to. And that depends, that group to group varies, depending on what you do. You may go work in a hierarchy, if you work for a postdoc, or,
Kind of grant it is like just join something to start.
Yeah, when it's a stylistic thing, I think if you go work in like a huge group, you're going to have to work for a postdoc because of time management of the boss. But in a smaller group like mine, it's a flatter organization where it's more independent and stuff. It's a sort of stylistic thing.
Yeah, so this other group that originally published this paper, research on, have you had any like communication with them? I'm just curious what the dynamic would be.
Yeah.
Here's this grad student that may be trying to validate,
Right.
some large result they have.
Right. Probably the only thing that I've done that I can definitively say really impressed my boss was getting a meeting set up to meet with this guy. I was at a conference. I happened to be sitting next to him in the room. I didn't even know that he was necessarily the guy. I just kind of guessed because he was asking very fervent, very aggressive questions to people who were contradicting the results. So I was like, hey, I work for Dan. Could we maybe talk a little bit? And so I set up a meeting. We did meet with him. And he's super supportive. They're very helpful. They want to share and help as much as they can. But there's a lot that they can't help us do. He knows that like his research is really needs support or like confirmation from other people, because it's a very ambitious claim that has very much not really been replicated. And it's been like 10 plus years now. So he would love to and is very supportive of helping people, but yeah, I don't know. There's a lot he can't do for us. And most of it, I mean, is the lasers themselves cost millions of dollars. So like how many people have the capabilities?
And do you know any other like groups working in the area?
I don't. I hope that no one's doing exactly the same thing as me. I don't know. I know that the grant that we got that specifically funded this was a whole program sort of inspired by the work out of Germany from Andrea Cavalieri. And there were a bunch of people who were funded to do various related things, but I believe I think they kind of all lost their funding because they were all too ambitious. But I could be wrong about that. Yeah. Yeah.
So you mentioned there's a lot that you do in cellular physics. How much of the equipment that you're working with is like your own design?
Yeah, that's a good question. I wish more of it was commercial, because that stuff works. A lot of it's commercial, but one of the things that I made was like we needed to deal with stabilizing our laser pointing pretty precisely. So I sort of found some cameras and built an optics setup to image that pointing. Got some piezo mirrors, and then connected all the electronics up. All these things, cameras I didn't make, piezos I did not make. Right? Those are commercial, but put it all together, created a software platform to sort of bring in that data and do a feedback loop to stabilize that pointing. So that was something that I kind of made. It was inspired by other people that had done similar things for sure. But that was something that I made. A lot of, our ARPAS system is mostly designed in home, like that giant chamber I showed you, not by me, by former students and our staff scientists. So I don't know what the right number is. It's probably like 70% is at least commercial, just because so many different components are commercial. But then maybe slapped together by students and postdocs and stuff like that for various niche applications. Yeah, so what happens is, like I said, it tries to expel the magnetic field perfectly, so there's no magnetic field in it. But we know from quantum mechanics that it's very hard to totally get rid of something because there's these like little fluctuations and things going on. And so what happens at a quantum mechanical level is that the magnetic field itself sort of flux quantum pop into existence, and the motion of those little quanta of magnetic field would cause dissipation and would cause issues for the superconductor. So what happens is those little flux quantums get locked in place inside of the material. And it is the locking of those flux quanta that locks the whole system, right? The whole system can't move because of that magnetic field locking. It's called flux pinning or quantum locking, or two different names for it. There's some good tech talks on it if you want to try and read a little bit more, watch a little more on it. But yeah, it's because of this attempt to expel the magnetic field, but the quantum reality that can't do that.
Well, if anyone has more questions, you can talk to Garrison afterwards individually, but if not, let's thank you.